Hi everyone, in this video I'll be going over section 3.4, and for some reason I don't think it'll flip over to me, so I might just have, to have you stare at the screen while you listen, so sorry about that. Okay, so with 3.3 and 3.4 I actually tend to change the order of the book just a little bit, and that's because 3.4 is about the chain rule, which I'll talk about in a minute. 3.3 is about trig functions, and usually people kind of catch the concept of the chain rule a little bit better when it's not introduced at the exact same time or with the trig functions, just because a lot of people tend to forget trig a little bit more than they tend to forget some of the algebra and things needed for the chain rule. So the ordering's a little weird, but what we're going to do is do 3.4 part 1, which is going to introduce the chain rule without trig functions. Then in section 3.3, I'll introduce trig functions. And then in section 3.4, part 2, I'll introduce trig functions and the chain rule together. So that will be sort of the ordering of things. But let's start with the chain rule first. So thinking about the chain rule is what we use when we have a composition of functions. So to remind you what that is, a composition of functions is when you have one function that sort of fits inside of another function. So the way that we write this in, pre-calc, algebra, pre-algebra, etc., is f of x. So we could write that as f of g of x. Sorry, I meant f of g of x. Or some people will call it fog, but really it's f, that little o means of g. So it essentially means you have one function, in this case, g of x, fitting inside of another function. So we say a composition of functions. All right, one thing to recognize is that if I read to you f of g of x, that means that it's a composition. So sometimes people will think this means f times g of x, but that's not what we said verbally. So it's going to be really important to distinguish that. Okay, so quick example just for prereqs. Basically, how do you plug a function inside of another function? We've done this a lot with the limits, but I'll go over it just in case. So if I have f of x equaling to 2x squared and g of x equaling to x plus 1, if I want to find f of g of x, I need to substitute g of x inside of this function. So I'd get f of, and then g of x is the x plus 1. So now I have to run the x plus 1 through the x in my f of x equation to get 2 times x plus 1 all squared. So now I see I have this little x plus 1 function fitting inside of this larger polynomial function. Okay, so before we move on, I just want to think about this logically. A lot of times people say, oh, why do we need this? Or why does it make sense? Let's think about why this makes sense in context. So basically what a composition of function does, it accounts for one function changing in regard to or with respect to what another function doing, where they're both dependent on the same independent variable. So I don't know if I typed this or not, but I'll say it verbally. I did type it. Okay, so if we think about a person diving, for example, when they dive and go underwater, I think we probably all understand that the water pressure on that person is going to increase, and the water pressure really in general increases. So what we say is, all right, well, as this person is swimming down, we know the water pressure is also increasing. So that water pressure depends on that swimmer. If the swimmer swims faster, meaning the rate of change of the swimmer increases, we know that water pressure is going to increase more quickly as well, because as the swimmer gets deeper, the water pressure increases. So we can see that the rate the swimmer goes down affects the rate of the water pressure, and we know that rates in general are calculus, they're derivatives. So it's kind of one example where you could see a composition of functions. As you could probably imagine, there are a lot of things in real life that depends on other things, so it's a pretty applicable type of function. Okay, now I want to get to the computational part of this. So first I'm just going to introduce something that we've seen before, that we know, that was actually, I think it was either on the worksheet or maybe in the homework, but the function h of x equals e to the 2x. So a couple of people from your class said, oh yeah, let's use the chain rule on this. I was like, well, we haven't even talked about that. And then somebody I talked to said, oh, it's kind of like magic. Like the front number just drops down. It's like, yeah, it seems like magic, but we want to know really like why that's true, what's going on. So first, let's just consider e to the 2x. We've seen before that this is the same thing as e to the x times e to the x. So if we wanted to, we could use the product rule on this. So let's say we went through, we're like, all right, let's use the product rule. I guess I used h instead of f there. Okay, so put a little h in there. All right, So I have h prime of x. If I spell out the product rule, I know that is the derivative of e to the x, so the derivative of the first times the second, so times e to the x plus the first is e to the x times the derivative of the second is e to the x prime. This would give us e to the x times e to the x plus e to the x times e to the x, which is a little tedious, but it's the same as 2e to the 2x. All right, so what's going on here is we can add these together since it's like terms. That's how we get the 2. And now for e to the 2x, we have the same base here. You can add the exponent. X plus x is 2x. So of course we see we can get that using the product rule. If we wanted to use that, we could absolutely do it. But there's actually an easier way, and that is to use the chain rule. Okay, so let's notice with this that if we consider the whole function, that is e to the 2x, if we wanted to, we could write h of x equals e to the 2x as e to the x squared. Okay, that's just properties of exponents. So now notice that you have an e to the x inside of this bigger squared function. So here e to the x fits inside of that squared function. Okay, so I would say our inside function, or sometimes I call it our little function, is e to the x, and our outside function, or sometimes I call it our big function, is that squared function. So I think of big function as parentheses squared, little function is e to the x. Okay, hopefully you can kind of see how those fit. All right, sometimes the book, people will give it other names. So here we're just naming e to the x v and saying v is just some function. You can do that if you want. I tend to just leave the parentheses because I feel like the less notation generally works better for students, but it's totally up to you. All right, so for this first one, I'll use slightly more formal notation. After that, I'm going to simplify it a little bit and only use the formal notation when we kind of need to. All right, so first, notice that if we take f prime of v, so we defined f of v to equal to v squared, that's really the same thing as 2v. If we look over here at our v function and take the derivative of that, that's really the same thing as the derivative of e to the x, which is just e to the x. All right, now let's sub v back into our f prime equation. So we know we have f prime of v is equal to 2v, where v is equivalent to e to the x, right? That would give us 2 times e to the x, and I don't really need to write the parentheses there, but I did. I'll just write that as 2e to the x. It's the same thing. Okay, so we have that little part of it. All right, now if we take this and multiply by g prime of x, what we get is f of g of x prime, okay? That is the derivative of this composition of functions. I probably should put that prime around the whole thing, sorry. Okay, f of g of x prime is equivalent to f prime of g of x times g prime of x. Right, now I'm going to substitute, so I get 2e to the x, because that's what f prime g of x is equal to, times g prime of x, we found to be e to the x. Right, notice for that we get 2e to the 2x, which is exactly what we got when we use the product rule. Right, so what we've just used is actually the chain rule. Usually I use less notation, so I'm going to, but I will formally introduce the chain rule, which is what we use on compositions of functions. So key thing, if we have a composition of functions, okay, what we really do is take the derivative of the outside function, that was this right here, right, plug the inside back in. I'll do that in a different color. Say plug the inside back in. That's what I did right here. All right, and then we multiply it by the derivative of that little inside function, which was g of x. Okay, multiply the result by the derivative of the inside function. All right, so spelled out as the chain rule. Okay, if we have a composition of functions that are all differentiable, we say that f prime of x, it's like our big function, is equivalent to little f prime of x. Plug the inside back in, and then multiply by g prime of x. So the way that I usually say this is, let's take the derivative of the outside. So this is the derivative of the outside. Okay, which you do first. Okay, then you plug the inside back in. So plug the inside, or you could say the little function, back in. All right, and then third, do 2 here, you multiply by the derivative of the inside. Okay. Okay, so interchangeably, you could say big function or outside function. You could say inside function or little function. It means the same thing. All right, what's going to be, where this equation comes from, you've seen that it works for sure once, but of course we want to realize why it's always true. I've already explained why the concept behind this makes sense, but if you want a formal proof of the chain rule, you can check out this Khan Academy video, and it'll basically start with that same definition of derivative formula, go through all of that, and then the chain rule is what ends up peeling out. So if you're curious, please do look at the proof of why that's true. Okay, now I basically just want to do several examples. Something that you'll need to be very aware of when you do this is that it can be tough to figure out, at least at first, what your inside function or your little function and what your big function or your outside function are. So try not to get frustrated. You'll have to play around with it a little bit. It's totally normal. Be expecting it. All right, so first example. Let's consider the function h of x being equal to e to the negative x. And let's say that we want to calculate h prime of x, so the derivative. Okay, so on this, we've seen before that if I wanted to, I could change this to 1 over e to the negative x, and I could use the quotient rule. That's more tedious, so let's try to use the chain rule on this. All right, so just like what I looked at before, e to the 2x, I could rewrite this, which I'm going to. So notice that h of x is equal to e to the x raised to the negative 1. All right, so once I see this, I should see that my outside function, okay, my big function is what I have to this negative 1 power. Okay, so the outside function or your big function is your parentheses to the negative 1. All right, your inside function is this little guy that fits in here, and that's e to the x. So e to the x is your little function or your inside function. So I'll just write little function. Okay, so sometimes people will ask, well, why didn't you say that your outside function was e to the x? Don't write this down, but I'll explain. So if my outside function is e to the x, okay, I want to get the negative 1 back in there. How am I going to do that? If I plug in a negative 1, then I'd get e to the negative 1. And I know that's not the same thing. And also, I can't really plug that into here. And I also can't just throw parentheses in and write it to the negative 1 because it's not the same thing. So what you need to have happen is to make sure that you can substitute the little function back into the big function and have it be equal the same thing. In this case, if you chose e to the x to be your big function, you'd go to try to substitute to get that negative 1 in there and you wouldn't be able to. So that would clue you in like, I probably made the wrong choice here. So you have to play around with it a bit. As you see more, you should get more comfortable. Okay, so let's move along with the process here and perform the actual chain rule part of this. So I have h prime of x is equal to. All right, in words, I need the derivative of the outside or the big function. So I decided my big function was parentheses to the negative 1. I'm going to take the derivative of that. I can use the power rule because I have some variable per se raised to the negative 1. So I'm going to drop the negative 1 down, rewrite my fake variable, my parentheses, and raise that to the negative 1. All right, so I have the derivative of the outside right here. Deriv of the outside. Okay, and now I need to plug my inside back in. So I need to take my inside, which is e to the x, and plug it back in. So I need to plug inside back in. Right, now I need to multiply that by the derivative of the inside. Okay, so I decided my inside was e to the x, so I need to multiply this by e to the x prime. So now I'm just going to write that nicely all together and take my derivative. So this is equivalent to negative e to the x raised to the negative 2 times the derivative of e to the x is just e to the x, so times e to the x. All right, notice I have the same base, e to the x and e to the x, so I can just add the exponents. Sorry, I guess I should simplify this real quick here. So this is the same thing as e to the negative 2x by properties of exponents. That'll make it easier to follow. There we go, e to the negative 2x. All right, so I'm going to add my exponents, and when I do so, I get negative e to the negative x. All right, so we've seen that before. Hopefully it makes sense. So that -1 doesn't just drop down like magic, it is because of the chain rule. So now we know why that -1 appears to just kind of pop down there. All right, let's try another one. This one might appear a little bit more tricky, but we'll work through it. So this time, this example 2, let's consider h of x. Consider h of x being equal to e to the x squared, so e to the x squared, and we need to calculate h prime of x. All right, so again, when I read this, I have e to the x squared. All right, I can't rewrite this as a product because I have x squared. I don't have e to the 2x, so I know I can't bail out by that. This means that I'm going to have to use that chain rule. All right, so sometimes, don't write this down because it's not correct, but students will say, okay, so I have e to the x all squared. That's not true, right? E to the x all squared is equal to e to the 2x, which is not the same thing as e to the x squared. So I can't use that trick, which means this isn't going to be the exact same as what we saw previously in these notes. Right, so there's no way to write the e to the x inside of anything here, but if you think about it, okay, this x squared up here is actually a little function in itself. So let's see what happens if we switch this and if we can get an easy substitution. All right, so if I say, okay, let's have e to the u be our big function, where x squared is equal to u. That would be our little function. Okay, let's check to see if this makes sense, if this works. So basically, if I plug x squared back into e to the u, do I get the same thing I started with? So check. Let's see if x squared is equal to u and I plug that back in, I get e to the x squared, so that's good. All right, now thinking, did I make good choices? Well, if I took the derivative of e to the u, I know how to take the derivative of e to a variable, so I'm good there. I know how to take the derivative of x squared, so I'm good there. All right, so now we go through our process. So I have h prime of x. I need the derivative of the big function. So the derivative of e to the variable is always itself. So the derivative of the big function is equal to e to the u. Okay, so that's the derivative of the big. However, I need to plug my little function back in, and remember my little function was x squared. So now I need to plug that back in. I'm going to erase the u, plug the x squared back in. Okay, so plug little back in. All right, now I need to multiply by the derivative of my little inside function, so that is by x squared prime. All right, so let's write that a little bit nicer. When we do so, we have h prime of x is equal to 2x times e to the x squared. All right, so at this point, we've fully taken that derivative. Like I said, it can be a little tough to choose what to do and when, but play around with it, see what you can substitute in nicely, and then see if you are actually able to go through and take the derivative after making your substitutions. All right, let's try another one. This time, let's consider the function h of x being equal to e to the 2x plus 1, and we're going to calculate h prime of x. All right, so if I were you, this is really similar to the last one, so I would pause me and see if you can work through this on your own, and then see if you get the same thing as me. If you want, you can just watch me go through it, but it'd probably help your thinking if you gave it a try. All right, so thinking about this like last time, I know I can't just take e to the x and raise it to something here. I have that whole 2x plus 1 in the numerator there, which means that I'm going to have to use the same thing and have e to the u be my big function. So my big function is going to be this whole thing with my little 2x plus 1 function on the inside of it. All right, so here I know that my big function is going to be e to the u, where my little function is u equals 2x plus 1. All right, and here I'm not using the parentheses notation because it's a little harder to see, but if you wanted to, you could write e to the parentheses instead of e to the u. that part doesn't really matter. Okay, so let's take our derivative, h prime of x. All right, we need the derivative of the outside, so the derivative of e to the u is just e to the u. Okay, so in blue I have the derivative of the outside. Okay, I need to multiply that by the derivative of the inside. Or sorry, no, I don't. I need to plug the inside back in. So plug inside back in. All right, so I'm going to plug that little u back in, and I decided that was 2x plus 1. And again, you could just write a little parentheses there instead if you wanted. It's up to you. Okay, now I need to multiply by the derivative of the inside. So I have times 2x plus 1 prime. So let's do our finishing steps on this. So when we complete this, we should get h prime of x being equal to e to the 2x plus 1 times 2. So I guess I'll just write the 2 out front. That looks a lot nicer. Okay, the derivative of the inside of that was 2. All right, so hopefully you tried that on your own. You got it, you crushed it. If not, hopefully the explanation made sense. All right, one little tip or little note there is that oftentimes polynomials, not always, just like we don't say always a lot in this class, but oftentimes polynomials actually end up being that little inside function. So tip, okay, this is not always, but oftentimes, okay, the polynomial, so 2x plus 1 is a polynomial, ends up being your little function, or you could say your inside function. Okay, so that is not always the case, but it is often the case. All right, let's try something that looks a little bit different now, meaning not an exponential function. I think these are generally a little bit easier for people to see, but I guess you can be the judge of that. Okay, so this time let's say that we have h of x equaling to parentheses x squared plus pi to the 1/2. And we want to calculate h prime of x. All right, so when I see this, all right, I know that I'm not multiplying, so the product rule doesn't apply. I know I'm not dividing, so the quotient rule doesn't apply. I know I don't have something as simple as just a variable raised to a power, right? X squared plus pi is not just a variable by itself. And I know I don't have something as simple as a constant raised to a variable. So I know nothing from section 3.1 or 3.2 work. I recommend when you first start going through these, go through a little checklist. Like, can I use this? Can I use this? Can I use this? If the answer is no, which is the case with the previous material, then it implies I probably need to try the chain rule. And with this, I can see that, maybe I can see that, maybe you can see that, we have one function that fits inside of another. So if you look at this, can you tell me which function is on the inside? Which function fits inside? Right, maybe you said, oh, the x squared plus pi is on the inside of parentheses, so that is going to be my inside function. Okay, which means that parentheses to the 1/2, so the to the 1/2 part is your outside. Okay, so we selected our inside and outside functions. Let's go ahead and take the derivative. So we have h prime of x equals, all right, I need the derivative of the outside, so that's the blue part, which is the parentheses to the 1/2. So I'd have 1/2 times, I'm just going to put parentheses for now, to the negative 1/2. So I just use the power rule on that part. All right, now I have to plug the inside back in. So my inside is x squared plus pi. So I took the derivative of the outside and plugged the inside back in. Now I need to multiply by the derivative of the inside, which we decided was x squared plus pi. So I'd have x squared plus pi prime. Right? Let's go ahead and finish this out. Already done with my first part, so I can rewrite 1/2 x squared plus pi raised to the negative 1/2. Take the derivative of this inside part, so I'd have times 2x. Right? Honestly, you can stop here, but this is a pretty simple simplification. So I'm going to go through that. So 1/2 times 2 is just 1. might as well just multiply those out, and then I'm going to pull the x out in front because it looks nice, but it's not really necessary. I could have stopped at this step right here. Okay, so kind of nice when you have whole parentheses like that raised to something, because then it's usually a lot easier to see what to do. Notice again, our little polynomial here ended up being our little function. So like I said, it doesn't happen always, but it is fairly common for that to happen. All right, also note that in the back of the book, or if you're using WebAssign, you'll probably have to simplify this more. So my guess is they'd make you drop this negative exponent or this whole term into the denominator and possibly rationalize the denominator. I'm not sure exactly what WebAssign does, but I know the back of the book simplifies more than that. All right, let's go ahead and do another one. So this time, let's consider w of x being equal to x squared plus 5x divided by x plus 1, and say we want to calculate, or I'll say find w prime of x. All right, so the first thing I'm going to say is this should look familiar. If you wanted to use the quotient rule on this, you absolutely could. So I'll take note of that. If you wanted to, you could use the quotient rule. Could use the quotient rule. Okay, but let's say you don't want to use the quotient rule, you prefer to use the product rule, right? So you could also, or I'll say you could instead, rewrite as w of x is equivalent to x squared plus 5x times x plus 1 to the negative 1. All right, so when I introduced the product rule, when I tried to do something like this, I said, I can't do this. I don't know how to take the derivative of something that's raised to a power, so a whole polynomial that's raised to a power. Well, now I do know how to do this. I know I can use the chain rule on this, so it is an option to use a product rule on something like this. All right, so let's go ahead and take the derivative. All right, first I see, if I read this aloud to you, I would say I have x squared plus 5x times x plus 1 to the negative 1, which means that I am going to be using the product rule. So let's write out the product rule. By the product rule, we have that w prime of x is equivalent to, right? We have the derivative of the first function, so x squared plus 5x times the second function, so times x plus 1 to the negative 1, plus the first function, so x squared plus 5x, times the derivative of the second function, so x plus 1 to the negative 1 prime. All right, let's go through and actually take our derivatives. So we have w prime of x is equal to, the derivative of the first one is nice, should look pretty familiar. We just have 2x plus 5x. Okay, then we'll rewrite the x plus 1 to the negative 1, plus rewrite the x squared plus 5x. All right, now we need to take care of the derivative of x plus 1 to the negative 1. All right, so try to look at that and think, what's your little function? What's your big function? Okay, you should have decided, hopefully, that your little function or your inside function was x plus 1. Okay, your big function, or you could say your outside function, was that parentheses to the negative 1. So that's your outside function. Okay, so if we take the derivative, we'd multiply by the derivative of the outside. So that would be negative 1 parentheses to the negative 2. We have to plug the inside back in. So I'm going to put that x plus 1 back inside. And now I need to multiply that by the derivative of the inside. So I'd have x plus 1 prime. All right, so let's complete that and write our answer. So I'll rewrite everything that we started with very quickly. You can fast forward through me if you want to on this. Plus 5x minus, no, that's times a negative, sorry. So let's pull that negative out in front so we don't get confused. All right, if you leave that negative 1 there, you need to write times the negative, or else it looks like you're subtracting when you're not. I'm just going to pull it out in front to not have to deal with it. Okay, so times x plus 1 to the negative 2, and let's take the derivative of x plus 1. The derivative of x is just 1, the derivative of 1 is 0, so technically we could write times 1, but that's not necessary because it just equals the same thing anyway. So we have completed this. This is our final answer. Again, if you look in the back of the book and probably on WebAssign, you'll need to simplify that more, but we've completely taken the derivatives, so I'm happy with that answer. All right, and I'm already getting a little lengthy with this, and I think my computer is kind of heating up and making funny noises that I hope you can't hear. So I'm gonna stop this one, and then in the next video, I'll do a couple more complicated examples. At that point, you'll be able to hop into the 3.4 Part 1 homework.